Okay, guys, so we just finished this significance test for Skittles, deciding whether or not we can actually tell the difference better than just guessing. So there was the conclusion that I just wrote in, and then I also wrote in the big ideas, and these will be posted, but I'm going to go over them real quick. Learning target number 7 is about constructing, or about performing, I should say, a significance test for population proportions P. So it has the same 4-step process. You state, but now what you state is different for hypothesis test than it was for confidence intervals. So for hypothesis test, you need to state the perimeter, the statistic, the hypotheses, both of them, and then your significance level alpha. In your plan, it's similar. You need to name the procedure, although the name is different now, and then check the conditions, which are the same as it was for confidence intervals for P. And the do step, it fits that same general outline. We write down the general formula, then the specific formula, but now we have to show a picture, and then we plug in our numbers and write our answer. And then in the conclusion is definitely different. We're no longer interpreting a confidence interval. We are deciding whether to reject or fail to reject the null, and thus we do or do not have convincing evidence against the null. Again, instead of saying against the null, you can say for the alternative, right? If it's for the alternative, then that is against the null. They're the same thing. Okay, so what is new here is our test statistic, right? I'm abbreviating this to just stat. The test statistic for proportions is the statistic p hat minus the parameter p divided by the standard deviation for sample proportions, which is that square root of pq divided by n. Okay, this is the general formula. So I might even sketch that on here. The general formula here is the formula for test statistic. And then the specific formula for proportions is this Z test statistic, okay? Then you would fill in your work, and the picture you would draw is your normal curve. So the last little part to mention here, we have not seen a two-sided test yet. So far we've seen a less than, a more than, and now we're gonna see a not equal to, so a two-sided test, right? We're going to have an alternative hypothesis that it's just not equal to the null. Whenever we do that, we have to multiply our p-value by 2. So that might not make a whole lot of sense right now, but hopefully after seeing this problem, when you come back up and look at this, you'll be like, oh yeah, okay, we multiplied the p-value by 2. Okay, so our problem for the Check Your Understanding says, according to the National Institute for Occupational Safety and Health, job stress poses a major threat to the health of workers. So a news report claims, they use that word claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. So already I'm kind of thinking, I bet that's my null hypothesis, because that's what they think is just kind of like the standard. So I keep going. Managers of a large restaurant chain wonder whether this claim is valid for their employees. So a random sample of 100 employees, all right, take it good, it's a random sample, and I know what my sample size was, finds that 68 answered yes when asked. Okay, so if 68 answered yes when asked, does work stress have a negative impact on your personal life? I now also know the sample proportion who answered yes. 68 people, but then my proportion is going to be that 68 divided by the 100 in the sample, okay? So I can tell that's 68%, right? So I'm already thinking, 68% is not as high as 75%. So there's some evidence that the percent of restaurant employees who feel this way is not as high as 75% for this restaurant chain. We need to determine whether that is enough evidence to be convincing that it is less. So that's our question. Do these data provide convincing evidence at the alpha equals 0.10 significance level? Look at that. We aren't using 0.05 this time. We switched it up. That the proportion of all employees in this chain, notice I'm specifying my population as just employees in this chain, who would say yes differs from 0.75. And this is what is so important for making our hypotheses. Instead of saying being lower than, not being enough, being more than, all of those different inequality things, this says differs from. So it's not specifying that it's more than or less than, it's just different from in general, is what they're curious about. Okay, so let's state what P is. This is going to be the true proportion. Let's see, they're interested in of all employees who would say yes. Okay, so of the chain's employees who would answer yes. I could put to that question, but I'm trying to be a little bit brief here. Okay, so then my statistic is my p hat, my sample proportion, and I saw that it was 68 people out of the 100 said yes, which would give me 0.68. Now, obviously that is different from 0.75, but that's just from the sample. I want to know if that sample is far enough from 0.75 to convince me that the whole population must have a proportion different from 0.75. Okay, so my hypotheses then, H naught, the null hypothesis, is that nothing is different. It is 0.75. So P equals 0.75. And then my alternative hypothesis is still going to be about P, and it's still going to be with respect to 0.75, but then I have to decide whether I think P is less than, more than, or just different from. Now, if this phrasing had not been here, and I just knew my sample proportion, I would think, oh, I'll see if it's less than. But it specifically asked me just to see if it's different from, so I put not equal to. Okay, not equal to. That's different from 0.75. And then I have to state my significance level, which the problem told me to use alpha equal to 0.10. Okay, so now I need to name my procedure. Hopefully you remember the name of this test is a one sample Z test for P. Okay, and then I have to check my conditions. So the first one is whether or not I have a random sample. And somebody asked me in a discussion post, what would you do if you didn't have a random sample? Well, you should not continue. If this is the real world, you could go ahead and run the test, but at the end you'd have to say, I'm not actually sure if these results are valid, because I cannot be sure that my sample is representative of the whole population. So it's a good thing that we do have a random sample of 100 employees. And I'm putting this in quotes because I'm quoting exactly from the problem statement. Okay, so that condition is met. The second condition is my 10% condition. So I know that my sample size is 100, and that is, let's think, I need that to be less than 1/10 of the population. And my population is all of the large chain's employees. So when I think of a large restaurant chain, I'm thinking like a McDonald's, a Wendy's, could be something a little bit nicer, maybe an Applebee's, something along those lines, right? So they definitely have a lot more than 1,000 employees in their entire chain. So 1/10 100 is indeed less than 1/10 of all of the large restaurant chains employees. Now, that condition would not be met if, say, we were talking about, I don't know, Ted Drew's. I doubt Ted Drew's has 1,000 employees. And so a sample of 100 would be too large to fit this 10% condition. But we're dealing with a large restaurant chain, so we're good. Okay, so then the third condition is to see whether a normal model fits for this. And of course, we use large counts to find that out. So I calculate N times P, or 100 times the population proportion that I'm assuming, which is 0.75. It's easy enough to calculate. I know that that's 75, which is of course greater than or equal to 5. So N times Q would be 100 times 0.25, or 25, which is also greater than or equal to 5. Done. Okay, all conditions then are met. Okay, so now I'm ready to move on to the do step. I start with my general formula. So my test statistic is equal to a statistic minus the parameter divided by the standard deviation. And then I fill in what my specific formula is for proportions. So it's a z-score, or a z-test statistic, equal to the statistic of p hat minus the parameter of p divided by p times q divided by n, the square root. Okay, so that's my specific formula, and then I could go ahead and fill in my values for the work for calculating that z-statistic. But before I do that, I would like to draw out my normal curve. And so I actually am going to draw this one during the video. So let's see. Trying to give myself enough room here. Remember that your normal curves don't have to be perfect. Okay, so let's think. My mean, right, if I go back to my big ideas here on the previous page, my mean for this, right, the mean of sample proportions is p, and my standard deviation is that square root of p times q divided by n. So let's see, p for us we're assuming to be 0.75, so that's going to be my mean of my normal curve, and then I need to calculate what my standard deviation will actually be. So I'm just going to kind of do that out to the side over here. Excuse me. So I have the square root of 0.75 times 0.25 divided by 100. Again, that's my standard deviation for p hat. All right, so second square root of 0.75 times 0.25 divided by 100. I get 0.043. Okay, so that's what I'm putting as my other parameter here, 0.043. So now, I didn't make my normal curve very even, did I? I'll change right with the middle there. Say the middle is like here. Okay, so my mean is 0.75, and then I need to calculate 3 standard deviations above and below the mean. Notice I'm really more interested in below because that's what my sample proportion is, but I'm going to go ahead and calculate them all. So for this part, I am going to pause and continue in the next video. I want to go ahead and be able to write out those values, but I don't think it's worthwhile for you to watch me calculate them.